Welcome to this explainer, my astute apprentices. Step right into my study. Today we're facing a rather chaotic crime scene, a seemingly impenetrable wall of raw data. But we aren't just passive observers here, we're mathematical sleuths. By wielding the rigorous science of descriptive statistics, you're going to soon possess the analytical tools to transform absolutely any perplexing dataset into a clear, undeniable narrative. So, let the investigation begin. Here is our official docket of evidence for today. 1. Decoding the data mystery. 2. Finding the central tendency. 3. Measuring data dispersion. 4. Symmetry and kurtosis. And finally, 5. Sketching graphical summaries. Let's get right into it. Section 1. Decoding the data mystery, setting the scene.
Section 2. Finding the central tendency, the usual suspects.
We'll begin our inquiry by deploying our mathematical magnifying glass to find the exact center of our evidence. Now, you can keep your wits sharp in the field with these really simple memory tricks. The mean is the quote-unquote mean one, simply because it forces you to actually do the math. The median is just like the median strip on a highway, cutting the data perfectly down the middle. And the mode? Well, think MO for most frequent. It's basically our suspect's most repeated alibi. So let's examine the mean first. It's represented by the Greek letter mu for a population or x bar for a sample. You calculate it by taking the total sum of all your observations and dividing that by the total number of observations. It's an absolute workhorse for sure, but beware, it won't make a lick of sense if you're investigating qualitative clues like names or colors. The mean strictly demands numbers to work its magic. Now, what if our clues are neatly packaged in a frequency table? Don't let the mathematical notation frighten you. It's actually a very simple deduction. We just multiply each value, which here is the number of SIM cards, by its frequency. Then we sum all those products to get 162, and finally divide by our total sample size of 60. Elementary, we deduce a precise mean of 2.7. Our next suspect is the median. If we take all our scattered clues and sort them in a meticulous row from smallest to largest, the median is exactly the 50th percentile point. It perfectly divides our dataset right into two equal halves. Got an odd number of clues? Just take the one dead in the middle. An even number? Simply average the two middlemost figures. Easy as pie. Then we have the mode. Sometimes the truth is just a matter of sheer repetition. The mode is simply the value occurring with the absolute highest frequency. Unlike the mean, which can be totally thrown off by a single rogue outlier, the mode stubbornly focuses on what happens the most. Think of it this way. If our suspect claims they were at the pub 5 nights and the theater only once, well, indubitably, the pub is our mode. Section 3. Measuring data dispersion, tracking the footprints. Having successfully established the center, we must now track the footprints to see exactly how far our data wanders. The simplest deduction of all is the range. You merely subtract the absolutely lowest observation from the highest. So if your data points are 5 and 45, your range is 40. It's literally measuring the physical distance from the smallest footprint at the crime scene to the largest. But let's be honest, range alone is a bit too crude for a master detective. We require the standard deviation, denoted by the Greek letter sigma. This brilliant metric, which is derived from the square root of the data's variance, explains exactly how tightly our data clusters around the mean. A small standard deviation? That means our suspects are grouped closely together in one tight location. A large one? They've scattered wildly across the map. But what if we have to compare the variability of a suspect's income in dollars to their height in inches? To do that, we deploy the elegant coefficient of variation. By dividing the standard deviation by the mean, we generate a standardized ratio. This is fantastic because it allows for perfect apples-to-apples comparisons across entirely different datasets and different scales. Moving on to Section 4, Symmetry and Kurtosis, the suspect's profile. Two datasets might have the exact same mean and spread but present a completely different profile. We have to analyze their overall shape. As you'll see, skewness determines if our data leans heavily to one side, completely off balance. Kurtosis, meanwhile, reveals whether our data possesses sharp, acute peaks or is flatter, wider, and a bit more subdued. A brilliant detective knows you can easily be led astray by relying only on the mean or median. Skewness measures how unevenly data clusters compared to a perfectly symmetrical bell curve. If the data trails off to the right, creating a long tail, we say it's positively skewed.
Trailing to the left, negatively skewed. It exposes precisely where the hidden weight of our evidence lies. Kurtosis, on the other hand, reveals the extremes, the literal fatness of the tails. Leptokurtic distributions have acute peaks and thick, fat tails, warning us to expect extreme outliers, erratic suspects capable of wild deviations. Conversely, platykurtic distributions are wider, more cautious curves with thinner tails and fewer outliers. A standard Gaussian bell curve rests quite peacefully right in the middle.
Section 5. Sketching graphical summaries, the mugshot.
To close our case and present our findings to the jury, we must sketch a final visual mugshot of the culprit based on all our numerical evidence. Building a box plot is a masterful step-by-step deduction. First, you locate the median. Then, frame the middle 50% of your data between the lower and upper quartiles to form your interquartile range. Finally, you just extend your whiskers outward to catch the minimum and maximum values, neatly isolating any rogue outliers. Consider this ultimate suspect lineup. The histogram groups numerical variables into vertical bins, instantly revealing the overarching visual shape of the distribution. But for a truly comprehensive profile, take a look at the meticulously ordered stem and leaf plot. It provides a similar visual shape, but astoundingly preserves every single original raw data point, sorted by their leading digits. Truly marvelous.
So, my apprentices, we reach the end of our inquiry. A true statistical detective never blindly trusts a simple summary or a lone average. You must always deploy your measures of dispersion, your skewness, and your graphical mugshots to dig deeper and uncover the complete truth. The next time you're presented with a single number claiming to tell the whole story, I want you to ask yourself, what outliers, what peaks, and what hidden shapes are lurking beneath it? Class dismissed and happy sleuthing.